So this is the original form. Here we have the pressure. It should be measured in the absolute pressure, okay, not the ground pressure. And is the number of moles. Of course, the temperature should be measured in kelvins, and depends on the way we measure the pressure and the volume. The gas constant might have different units associated with different numerical values. This one I told you already, you should really pay attention on the units, not only for the gas constant, but also for all values. So each time you try to replace one value, you should write down also the units associated with this value, because physics is very different than maths. So with physics, no units means nothing. We can also rewrite the ideal gas law using the Boltzmann constant, okay? The Boltzmann constant. So please remember this constant and also the unit of this constant. So joules per Kelvin. Good. Joules per Kelvin. Now for the work done by an ideal gas, we have the work done at constant temperature. So please remember this. The work done at constant volume, of course, no expansion, no contraction. Then the system does no work added to the system, no work done by the system. Good. And at constant pressure, this one is also very easy. Yeah, P delta V. Phổ thông thì thường là chúng ta, các bạn là thường là nhìn công thức này, vì thời phổ thông thì là thường tính rồi các cái áp suất không đổi, được không ạ? Good. So this is our ideal gas. We also developed together expressions to relate the pressure, the temperature, and the root mean square speeds. Root mean square speed, I remind you once again, here, this is what we have developed together. I hope you remember we apply mechanics for the molecules, and then finally we should be able to find an expression to relate the pressure, okay, and the root mean square speed. Wait for me here. This one. This is the expression to relate the pressure made by the gas with their speeds. Here we have the root mean square speeds. This one is one thing you should remember. And here, this is the other one. So the root mean square speed can be written in this form. So you can calculate it. You see here, the mean square speeds of a gas depend only on the temperature and also the nature of the gas. When I talk about the nature of the gas, I talk about the molar mass, okay, of the gas, because each gas will have different molar mass. Okay, we did a small exercise to see the difference between the average value and the root mean square value already. And did we see this one also last time?
Yes, we did.
Good. Okay. Translational kinetic energy. This one is also easy. You see that the translational kinetic energy depends only on the temperature. Here. Yeah, it depends only on the temperature. It means that if we know the temperature of the gas, we also know the average translational kinetic energy of that gas. Okay. And what we see also is that at a given temperature, so all ideal gas molecules have the same average translational kinetic energy. So no matter what their mass, they have the same translational kinetic energy. We also developed an expression for the mean free path, right? The mean free path, the distance in average that one molecule can travel between collisions. So it can tell us, for example, the density of that gas. Okay. And we developed also an expression for this. Last time, someone asked me, why do we have the root square of 2 at the final expression? This one. So I recommend you to write down on the expression and then to develop by yourself once again. Okay, you reread my slides and then you recheck, then you will see why do we have the root square of 2 in this expression. I already uploaded my slides on Moodle also. So anytime you can redo this exercise. Normally during the exam, I do not ask you to re-demonstrate the formula. What I ask you is just to remember it. Okay, but what I need is that you understand from the basic things, why do we have this one? So in this way, you will remember much better. Okay. Normally, I think this year, you will also have a final exam online, not an offline exam. So if we consider the questions, it should be a little bit harder because I suppose that when you stay online, you might have some tools that will help you. So the level of the questions will be a little bit higher. So pay attention on it. Okay, I think we stop here, right? This one is new, right? The distribution of molecular speeds.
Yes, this is new.
Okay, and we continue here.
Yeah.
We just developed the formula to have the root mean square speeds, right? And we know that the root mean square speed is just an average speed. Of course, we have more speeds, more kinds of speeds that we can analyze. And regarding the speeds, we may have other questions. For example, what fraction of the molecules have speeds greater or smaller than the root mean square value, right? Because the root mean square value is only one speed. Then what fractions of the molecules will have a greater speed or a lower speed than the root mean square value? This is one thing. Then to answer this question, we need to know how the possible values of speeds are distributed among the molecules. Because for our sample, we consider a lot of molecules, and each molecule will have a different speed. Okay, we'll have a different speed. So it can start from 0, then the molecule doesn't move, and it can go to very high. Here I have an example of oxygen molecules at 2 temperatures. So one temperature at 80 kelvins and one temperature at 300 kelvins. So you see the distribution of one mole, okay, of the oxygen. So you see, for example, at 80 Kelvin, so very low, what do we have? We have the speed of oxygen molecules are mostly around 200 meters per second. Okay, the speeds of molecules of oxygen at 80 kelvins are mostly around 200 meters per second. When we raise the temperature, what we see is that, the speeds of all molecules are increasing. So you see, now the most probable speeds are around 400 meters per second. And also for the molecules that are having speeds close to 0, you see the portion. The portion of these molecules is also much smaller. Okay. So that how do we establish this kind of distribution? So in 1852, Maxwell, okay, maybe you heard about him, the Scottish physicist James Clerk Maxwell. He first solved the problem of finding the speed distribution of the gas molecule. You see the PV here, it has a name. Here, the distribution. So he developed the Maxwell speed distribution law. The PV, what you saw here, is actually can be calculated. And it depends on the molar mass, on the temperature of the gas. You see, only on the molar mass and on the temperature, we can find the probability distribution function. This one. Is it okay? This is one thing that I do not, how to say, demonstrate it because it's quite complicated. you should remember this formula, or I even consider to not to include this part in the final exam. But anyway, I show here for you. And you still have to remember, you still have to know that there's a speed distribution law developed by Maxwell, and it depends only on the molar mass and on the temperature of the gas. Normally, you know two things, you can calculate the molecular speed. Good. Okay, so we have the function. Xin lỗi, cái chỗ này không hiểu vì sao nhé. Lúc mà tôi để full màn hình thì hai cái biểu thức này nó không hiện ra. Tôi để nhỏ màn hình lại để cho các bạn xem nhé. Bây giờ các bạn thấy hai cái biểu thức chưa? Mình không hiểu tại sao tôi chưa fix được cái lỗi ở chỗ này. Okay, we continue. We know the PV already, distribution function. Then we want to see more. We retake the distribution of our oxygen, right? And please take a look at the picture. What do we have? We have the product PVDV, this one. Yeah, the column in yellow. This is actually the product PVDV. This is actually the fraction of molecules with speed in the interval dV. Okay, this one is the interval dV and centered on speed V. So we know this area in yellow is the product PVDV. Then the total area under the distribution curves here. We can calculate it. This is actually this formula, the integral from 0 to infinity, right, of PVDV, and this one equal 1. Is it okay? This one is always equal 1 because we are talking about the sum of all the fraction, okay, of all the fraction. So it should be 1. The fraction of molecules with speeds in an interval V1 to V2, okay, is up to your choice. Then it will be equal to this integral. If you want to consider a fraction of molecules with speed in a certain interval, then you can use this formula. Good. You just replace the expression of PV and then you solve the integral. Of course, you need to know a little bit of mathematics here. It's also a little bit complicated, but try to do it during the tutorial class. Maybe I will give you some exercises during the tutorial class for you to practice. Wait for me, I change it into full screen once again. Full screen. Okay, do you see it in full screen?
Yeah.
So
yes, but we still lost the
we lost the, I don't know why we lost the formulas. Anyway, we are done with this slide. Okay. Okay, I have to click. No problem. Then we reconsider once again our gas, oxygen. You see here, as I said, the root mean square speed is only one kind of speed. We can analyze our gas based on other types of speeds. For example, the average speed. Average speed, it has this formula, okay? And the most probable speeds, so it has this expression. Now, if we take a look at the figure, what do we have? We have the most probable speed is actually always the highest point of the distribution curve. This is the most probable speeds. So here we mean the speed that the molecules, our molecules in our sample here, the most probable speeds is actually the speed that the molecules will take the most. For example, if you have 1,000 molecules and you have, say, 500 molecules having the speed of 1,000 meters per second. You have 200 molecules having speed of 200 meters per second, and 300 molecules having the speed of 200 molecules. Then the most probable speeds will be 500 meters per second. Okay, so the name of this speed is also the meaning. Cái vận tốc mà các cái phân tử khí có khả năng là đạt được nhiều nhất. Có nghĩa là ví dụ như là tôi cho 1.000 phân tử khí, 500 thằng có vận tốc 500 mét trên giây, 300 thằng có vận tốc 300 mét trên giây, 200 thằng có vận tốc 200 mét trên giây. Thế thì cái vận tốc mà có khả năng xảy ra nhiều nhất nó là cái thằng 500, đúng không ạ? Đó, good. Và ở trên cái hình này thì nó bao giờ nó cũng là tương ứng với cả cái điểm cao nhất của cái distribution. For the average and root mean square speed is depends. Okay, it depends on the gas. It depends on the temperature also. Trong khi cái average và cái root mean square thì cái vị trí của nó phụ thuộc vào ga và nó phụ thuộc vào nhiệt độ. Okay, so we know that for a gas we can analyze the average speed, the root mean square speed, and the most probable speeds. So each speed will have a different meaning. And of course, different applications. We do not talk it here, but during the tutorial part. Now, please, I give you 5 minutes to try to solve it, this question. And then if you have the answer, please also send me using the chat box. We have our oxygen with the molar mass, you know already. So 32 grams per mole. At room temperature, but we say that the room temperature is 300 kelvins. Maybe it's a little bit different, but we make it in round. Then what we need to find is the average speed, root mean square speed, and the most probable speed. Try to do it. Yeah. Oh, thank you. We have the solution of Hồ Quang Anh. Yeah, Phú Huy also good. Okay, good. Now, here, this is the answer. So verify if you do it correctly. Oh, I'm sorry, here. Good. Then we can try to calculate the average speed and so on. Please remember, do not make mistake when you replace the values, okay? For example, when I give it in the molar mass, in gram, for example, in gram, then you should be able to know to convert it into kilograms. Otherwise, you may make mistake. You can rewrite the formula. So for example, R here is actually we use the SI unit. Then it has the units of joule per mole kelvins. But you can rewrite it in terms of kilograms, meters, cubic meter, and so on. Yeah. To have the meter per second at the end. So some people do not know why from this joule per mole Kelvin, and here we have kilogram per mole. Why at the end we have meter per second? Why, right? Then I recommend you to retake a look. How do we write the joule? Okay, the unit of joule is equivalent to another unit having the meter and second in the joule. Here we also have the same. Nhiều bạn không hiểu vì sao mà ở trong các cái biểu thức này nó chả có mét trên giây, mà tại sao lúc tính ra một hồi ông thay số cho các thứ một hồi, vào đây tới cuối cùng ta lại có mét trên giây, đúng không ạ? Cho nên là cái mà tôi khuyến nghị các bạn đó là xem lại một lượt cách biến đổi các cái đơn vị. Ví dụ như là joule có thể viết được dưới cái dạng nào nữa. Làm sao để cho nó hiện ra được cái mét trên giây. Nghe. Hoặc là ở đây là kg. Nhiều bạn thay luôn là gram vào, nếu mà cho ở đây là gram, thay vào đây thế là con số nó lệch đi hàng trăm lần. So here, the calculation is very easy if you understand well what dimension we are working on. Yeah. What we need to find is the speed. Then at the end, we should have also the unit of speed. But then how to have it correctly? And how do we have meter per second at the end? So it really depends on this way. If you write it grams here, it will be not good, right? Okay. Is there any question here? If no question, I continue. Okay, no question. Now we go to a very important part, the molar specific heat of an engine. And I'm sorry, an ideal gas. I would like to remind you once again, right? You know the specific heat already, right? The amount of heat required to raise or to lose the amount of heat needed to be added or to be removed from a substance to raise or to lower a unit of temperature. Then we have the specific heat. So the amount of heat that we need to add it to one more or removed from one more of a substance. We have the molar specific heat, right? So specific heat, molar specific heat, you learn it already. Now we consider the two specific cases of molar specific heat of an ideal gas. We have the molar specific heats at constant pressure and molar specific heats at constant volume. Ủa, bạn Vũ Ngọc Vinh làm sao mà cứ đung đưa molar specific heat at constant pressure, we call it Cp, and molar specific heat at constant volume, we call it Cv. Okay, we consider two special cases at constant pressure and at constant volume. What do we have for molar specific heat of an ideal gas? Now we consider firstly a monatomic ideal gas. By saying monatomic ideal gas, we say that we consider không thấy formula. Chắc lúc nãy thế chứ nhỉ? We consider a monatomic ideal gas. So do you see the slide? If you do not see it, please tell me, okay? Minh Vũ có thấy slide không?
Có.
Ông đang xem cái gì ấy? Bây giờ ông mới chuyển màn hình.
Em đang ghi lại mấy cái trên này ạ.
Không, Nguyễn Xuân Minh Vũ ạ.
Dạ.
Lúc gọi tới mới giật mình chuyển màn hình. Ông đang xem cái gì đi?
Em có xem gì đâu ạ?
Thôi, ông lại cãi gì? Chuyển màn hình thấy thay đổi độ sáng hẳn hot. Tập trung vào.
Dạ.
Tất cả các bạn tập trung vào nhé. Phần này là phần quan trọng này. Now, we have the monatomic gas. We have the diatomic gas and we have the polyatomic gas. Monatomic gas is individual items in the gas. So we have, for example, helium, argon, right? Diatomic gas, we have maybe oxygen because it has two atoms in the molecules. We have maybe nitrogen and so on, hydrogen, or polyatomic gas. So we have, for example, methane, CH4, or we have water, for example, H2O, and so on. Okay. For now, we consider only the monatomic gas because we start always from the easiest thing to develop our formula, and then we generalize to have a general formula. So for all gases. Then for the monatomic ideal gas, we assume that the internal energy of our gas is actually the sum of the translational kinetic energies of the atom. Why? Actually, for one atom, it can have different modes to store the internal energy. So it can store the internal energy from the translational kinetic energy, from the rotation kinetic energy, or even from the oscillation. Okay. So different modes, we will talk about it deeper in the next slides. But for now, we know that according to the quantum theory, the monatomic ideal gas will have only the translational kinetic energy, not the rotational kinetic energy. Good. Then in this case, we can assume that the change in internal energy is actually the sum of all the translational kinetic energy of the atoms. Good. Then we can write it like this one. Okay, the average translational kinetic energy of a single atom is actually also the internal energy of this atom. Good. Then if we calculate it for n moles of the gas, we should multiply with the number of molecules that we have in this amount of mole. So it means that we have to multiply with a factor of n and a. So this is the number of molecules that we have in our sample. Okay, then we have the internal energy of our sample. If we replace our Boltzmann constant, you know, right? We can have a new expression. So for a monatomic ideal gas, we have the internal energy of this gas equal this expression, 3/2 nRT. Okay, this is the internal energy of a monatomic ideal gas. Please remember it, and then we continue. You can write it down. Okay, Thắng, Huỳnh Quốc Thắng, for example. Just do not look at it. You should write it down with me, so you will remember much better for others also. Bạn Nguyễn Sơn Tùng với cả bạn Thái Bình có đây không nhỉ? Nguyễn Thái Bình có đây không nhỉ?
Có à?
Ấy của các bạn đâu? Camera của các bạn đâu?
Em đang bật rồi à?
Giờ mới đang bật.
Không, em bật nãy giờ rồi à?
Thế sao tôi không nhìn thấy? Các bạn Nguyễn Thái Bình thì sao? Cam của bạn đâu? Cam của bạn đâu? Ok, Tùng. Bạn Thái Bình, tôi chưa thấy cam. B11 nó làm gì mà bây giờ mới bật? Tôi nhắc bao lần rồi.
Em vẫn bật nhưng mà chắc là do cái
Tập trung vào, tất cả các thanh niên tập trung vào nha. We finish this part and then we take a break. Monatomic ideal gas is very simple. We continue. Once we have the expression for our internal energy, then we consider the molar specific heat at constant volume. We try to develop an expression for the molar specific heat at constant volume. Okay, please look at the figure. Now we consider our n moles. our sample containing N moles, right? At a certain temperature and pressure and constant volume. So we have this gas confined to a fixed volume here. Then if we raise the temperature of the gas from the initial temperature T to a new temperature T delta T, in our pressure volume diagram, it will be expressed like this. So this is the isotherm. This is a new isotherm. Đường đặc nhiệt. By raising the temperature at constant volume, then the pressure will also be raised accordingly, right? To a new pressure of P plus delta P. Okay, so you capture it. Then how do we calculate the heat? The heat, but we will have the heat equal this one. The heat equal N CV delta T. Actually, CV is what we need to find. Good. Okay. You remember in previous part we saw, what do we saw? Q equal MC delta T, right? Now we consider only N more. Okay. We do not know the mass, but we know that we have the N more at constant volume. Then the heat is related to the temperature change by this expression, Q equal N CV delta T. Then remember the first law. If we substitute this expression into the first law, what do we have? I give you 10 seconds. Try to re-substitute the heat in the first law.
Delta of internal energy will be NCV delta T minus the work.
Very nice. Thank you. Here, this is exactly what we saw. Thank you so much. And we continue. Now, what we know is that at constant volume, we have the work equal 0, right? If we rewrite it, we have only this one. The change in internal energy equal NCV delta T. Good. Then the CV, we have an expression. We have an expression for CV. This is the first expression for CV. Good. We continue. Now we just developed the expression for the change in internal energy for a monatomic gas. We replace it. Do you agree with me? Because the internal energy of a monatomic gas is equal the change of the internal energy depends only on the change on the temperature. Then if we add the delta here, it's still the same. We substitute this expression for change in internal energy. Then we will have the expression for CV, for a monatomic gas, right? And we even can calculate the value Okay, we can even calculate the value of CV. So now we see that the CV of monatomic gas is 3/2 R, our gas constant. And it has a value of 12.5, sorry, 12 mole Kelvin. Maybe I rewrite here. I'm sorry, I took it's a bit time to rewrite the formula. Otherwise, you will not understand well. Joule per mole Kelvin. Mole Kelvin. Nó cứ tự biến thành cái các bạn chờ tớ một tí, bởi vì cái số mol này nó cứ tự chui xuống dưới, nhưng mà cái mol Kelvin, cả thằng mol lẫn thằng Kelvin nó đều phải ở dưới mẫu số nhé. Wait for me a little bit. Yeah, it should be written like this. Good. This is the expression and also the value of molar specific heat at constant volume. I try not to go too fast. Wait for me, I make it in big screen, in full screen. Is it okay for now?
Okay.
Yes.
Here I show you the value of CV for monatomic gas. We saw it already. Now we see the CV for diatomic gas and for polyatomic gas. Okay, for what we see is that for diatomic gas, the CV will have a greater value. Why? Because to heat, okay, to raise the temperature of diatomic gas or polyatomic gases, because they have more atoms in the molecule, then we need more energy to heat the atoms. We need more energy to heat the atoms. Then we should have a bigger value of molar specific heat. Okay, we should have a bigger molar specific heat. For diatomic gas, for an ideal gas, the CV should be equal 5/2 times R. And for polyatomic gas, for an ideal gas, it should have the values of 3R. Please remember these values. So we know when we consider monatomic gas, and this is an ideal gas, we can have this kind of value. For diatomic gas, we can have this kind of value, and for diatomic gas, we can have this kind of value. So what we see here is that our model by the kinetic theory of gases is also a model, right? An ideal gas is also an ideal model, let's say. We see our model work quite well even for real gases if this is a monatomic gas. You see? Or if this is a diatomic gas. However, for real polyatomic gases, yeah, the model doesn't work quite well. Yeah, you see the difference is quite big. But anyway, if we look at here, we still see that it is still worth considering the ideal gas, because sometimes we can apply it, but in a lot of cases we can apply for the real gases also. You see here, for example, here we can still apply for real gases if the real gases are monatomic and diatomic gases. But for polyatomic gases, maybe the difference is big. Good. So, okay. Then here, there's another explanation. Yes, someone has a question. In the diatomic gas, in previous slides, I talked about the way our molecules can store internal energy, right? For diatomic gas, it can store the energy in form of rotational kinetic energy. Here, then it has more energy here. Yeah. Good. And here also. So when we add or we remove the heat from our molecules, this heat, for example, if we add it to our gas, and if we add our heat to a diatomic gas or to a polyatomic gas, then one part of it will have to go into the translational kinetic energy, right? And one part of it will have to use for the molecules to rotate also, or to oscillate. That's why we need more energy, we need more heat. And to increase 1 unit of temperature for diatomic gas and polyatomic gas, we need more energy in form of heat. Okay, we continue. If we want to find a general form for any ideal gas, for polyatomic gas, diatomic gas, or polyatomic gas, then we can have this expression for the internal energy, or for the change in internal energy. Now we see here once again the change in internal energy of a confined ideal gas depend only on the change in the temperature. Okay, Nhật Anh. Okay, so a change in the internal energy of a gas at constant volume depends only on the change in the temperature, not on what type of process produced the change. Here, this one you should remember for any ideal gas, for any ideal gas. Good. We have seen the expression for molar specific heat at constant pressure. Now we will see the molar specific heat at constant, at constant volume. Now we will see the molar specific heat at constant pressure. I did a mistake here. This is constant pressure. We write it as Cp. We will continue to see it after 10 minutes, after a break. Is it okay? After 10 minutes we will see each other.
Yes.
Okay.
Constant pressure. Okay, we resume. Please come back and let your camera turning on. I try to check randomly. Với lớp lý thuyết, bởi vì rất là đông cho nên là tôi không điểm danh bằng cái cách gọi tên như từng bạn như ấy một, mà tôi sẽ chỉ capture screen này, lấy cái list, và trong cái thời điểm mà tôi capture screen này, bạn nào mà không có camera thì tôi tính là coi như là vắng buổi lý thuyết. Và bạn nào không có tên trong danh sách thì dĩ nhiên rồi nhé. Thế thì ngoài cái chuyện đấy là tôi cũng sẽ check ngẫu nhiên xem là các bạn có ở đây hay là không. Đó, thì các bạn cũng chú ý. Good. Now we can continue. Đấy, mình định cho full screen rồi, nên mình sẽ phải share lại. Good. So do you see it in full screen?
Yep.
Yes. Yes.
Okay, thank you. Now we try to develop an expression for the molar specific heat at constant pressure. Then still our gas, okay, of n moles. But now we have a constant pressure, an initial temperature, and an initial volume. Good. If we raise the temperature from T to T plus delta T, like this, please look at the mouse, at constant pressure, then the volume will be raised accordingly from an initial volume V to a final volume V plus delta V. Okay, and we know also the work done by this process is actually this area, having the value of P delta V. Then we do similarly the heat related to the temperature change will be expressed by this formula, right? It's still the same, but now we have Cp instead of Cv because we consider the molar specific heat at constant pressure and we call it Cp. So Q equal NCp delta T. And here, what we can contrast is that the Cp should be greater than Cv, right? Because the energy must now be used not only to raise the temperature, but also to do work. Okay, for Cv, we just need the energy to raise the temperature. But for Cp, a constant pressure, we need energy to raise the temperature, but also to do work. Then we should remember that Cp is always greater than Cv. How much it is bigger, greater? And we take a look here. Now, if you want to relate the two molar specific heat, we can restart once again. Here we have the expression for the relationship between change in internal energy and CV. Here we have the relationship between the heat and CP. Good. And here we have the ideal gas law, PV equal nRT. Okay, this is what we have. This one we have, this one we have, this one we have. And what else? We know that the work done by a constant pressure can be written like this. And we replace the P here, the pressure here, using the ideal gas law. Then we can rewrite the work done by the gas at constant pressure. This would be written like this. Okay, constant pressure should be written in this form, nR delta T. This is for the work. Then we apply the first law once again. Now we replace the change in internal energy by this expression, NCV delta T. We replace the heat by NCP delta T, and we replace the work by nR delta T. We have this expression. Good. What we see is that, yeah, the N delta T will be cancelled out. This one will be cancelled out. Finally, what do we have? We have only CV will be equal CP minus R, or CP equals CV plus R. Then we see here the difference between CP and CV is exactly our gas constant. Yeah, the difference between molar specific heat at constant pressure and constant volume is the gas constant. Good. Here I summarize the relative values of heat for a monatomic gas and for a diatomic gas at two different cases at constant pressure. So I write it con P here, and at constant volume, and con V here. For example, here we have a monatomic gas. What do we have? The heat at constant volume for a monatomic gas will have this value. Okay. The change in internal energy is exactly the sum of the translational kinetic energies of the molecules. Then for monatomic gas at constant pressure, what do we have? We have this one. At constant pressure, this is the value, okay, of the specific heat, molar specific heat at constant pressure. And this heat is used to do work, okay, and to do the translational kinetic energy. Okay. So we see here the difference. It's exactly the work done by the gas. Good. For diatomic gas, we also have the two cases, the heat needed to raise the temperature at constant volume and the heat at constant pressure. Good. And this, the difference is also the work. Now the heat is used for the rotational kinetic energy and translational kinetic energy, not only the translational kinetic energy. And the value here for the diatomic gas is this one at constant volume. For the diatomic gas at constant pressure, it is this one. Okay. So here we summarize. If you remember this figure, you will remember the values and also the meaning of the specific heat at constant pressure and constant volume. Good. Is it okay until here? Now, please, we have 5 minutes to do the exercise. We have a bubble of 5 mole of helium. So we know this is a monatomic gas, right? So this bubble is submerged at a constant depth in liquid water when the water and then also the helium undergoes a temperature increase of 20 degrees Celsius at constant pressure, okay? And as the result, the bubble expands. Firstly, we need to find how much energy is added to the helium as heat during the increase and expansion. How much energy is added to the helium as heat during the increase and expansion. Then we need to find the change in the internal energy during the temperature increase, and also the work done by this gas, when it expands against the pressure of the surrounding water. Then please, if you have the answer, please also send it to the group. Bạn nào còn bật mic thì tắt hộ tôi nhé. Có câu hỏi thì ta hãng bật lên.
Teachers, your microphone is mute, so we don't hear what you are saying.
Thank you for reminding me. Like I just said that I received the solution of Huỳnh Quốc Thắng, and it's very nice. Truly speaking, I don't really care about the final result. What I care is the way you find it. So it is not good to send me only the final result, because one can very well solve this question, but others they do not yet understand. Then what I need is that someone send the way he finds the results. So others, if they still do not understand, they can like take a look at it. So next time, if someone send me, like I said, send me the solution, please send me the whole solution, the way you find the final result, not only the final result itself. Thank you, Thắng. Very nice. Good. So here we have 5 mole of helium. We have the change in temperature of 20 degrees Celsius at constant pressure. What we need to find is the heat, right? And we know that we can calculate it with the help of this expression, NCP delta T. And now we know, because this is at constant pressure, then we use CP, okay? And what do we know? Yeah, is that we can rewrite it like this one. Actually, we do not need to do like me. If we see this value already, you can write it directly. If you do not yet remember it, you can just remember the value of CV, and you can refine the value of CP also. For a monatomic gas, right? Then CV equal to 3/2R, and CP V plus 1 difference of R. Finally, we should be able to have this one if you substitute the values correctly. For the change in internal energy, then we have this one. Okay. Change in internal energy equal NCV delta T. Please here, caution. I have one remark. The change in internal energy is always true if you use this formula, okay? It not depends on the situation that you are at constant pressure or at constant volume. You can always use this formula. Cho biến thiên nội năng này, thì bao giờ các bạn cũng có thể tính được bằng cái này. Bạn dùng NCV delta T, không nhất thiết là nó phải là ở constant volume hay nó phải là constant pressure. Change in internal energy. And here, for the work, what do we have? Then we know that for the work at constant pressure, we can use this formula. Here we use the ideal gas law, or in another way, we can use also the first law. So you see the link between the first part that you learn and the second part, okay? And the final result is correct. But any question until here?
Teacher, I want to ask that do we need to convert the delta T from degrees Celsius to Kelvin?
For But because this is delta T, there's no meaning to convert it because we talk
okay.
about the difference, right? So actually the difference of temperature is 20 degrees Celsius also mean that the difference in temperature is 20 Kelvin. Okay, do not make mistake here. Do not say like 20 degrees Celsius plus 200 something. No, because we talk about the change in temperature. Đúng không ạ? Các bạn đừng nhầm ở đây nhé. Delta T thì là nó cái sự biến thiên của nhiệt độ, thì nếu là 20 độ thì có viết thành Kelvin thì nó cũng là 20 Kelvin, chứ nó không phải là 2 độ lại cộng bao nhiêu Kelvin, bởi vì mình đang nói tới cái sự thay đổi của nhiệt độ. Nó thay đổi 20 Kelvin hay là thay đổi 20 độ C thì nó cũng giống nhau đúng không ạ? Đừng bị nhầm ở đây. But anyway, nice question. Good, we continue. Now we consider the degree of freedom and the relationship between degree of freedom and molar specific heats. Then what is the degree of freedom? I'm going to explain to you. Now, like I said, the molecules with more than one atom can store internal energy in different forms, not only in translational kinetic energy, but can also in rotational kinetic energy or even oscillatory kinetic energy. Okay. Here I have the three models. Helium, that represents a monatomic gas. We have a diatomic gas, which represents oxygen, which represents diatomic gas. Sorry, my throat hurts a little bit. And polyatomic gas, we have methane. I'm sorry. Then we see that all three molecules can have translational motions. So it can move left, right, up, down. So I mean in three axes, in the space, right? And it can have also rotational motions. Rotational motions. For example, you see here, it can rotate. We see much more for diatomic gas and polyatomic gas. For monatomic gas, it depends. In reality, yes, it can have some rotational motions. But in theory, we do not take into account of the rotational motions for a monatomic gas. Okay, for a monatomic gas. And for the diatomic and polyatomic gas, they can have also oscillatory motions. So the atoms will oscillate slightly toward and away from one another. Then you see here, the way it stores energy, we call it the degrees of freedom. The degree of freedom. Here we have the theorem of the equipartition of energy, sự phân bố năng lượng. So every kind of molecule has a certain number of degrees of freedom. So the degree of freedom is actually the independent ways in which the molecule can store energy. So this is one part of the theorem of the equipartition of energy stated by Maxwell. Okay. Every kind of molecules has a certain number of degrees of freedom, which are independent ways in which the molecule can store energy. And each such degree of freedom has associated with it an average energy of half of kg per molecule. Okay. So if we understand here, then we look at our gas. For a monatomic gas or for monatomic molecules, it will have 3 degrees of translational freedom and no rotational freedom. I mean that the helium can move up, down. So this is the OX axis, left, right. This is the OX axis, and then they can move in the OZ axis also. So it has 3 degrees of translational freedom. Good. And it has also an associated energy, right, of 3 times half kg per molecule. So this is an energy associated with a monatomic molecule. So you see something is similar here. We have 3/2 here already. For diatomic molecules, what do we have? We also have 3 degrees of translational freedom and 2 degrees of rotational freedom here. So it can rotate like a top, only about the axis, or it can rotate like this. Then the associated energy with a diatomic molecule is 5 times half kg. And for polyatomic gas, here we consider our gas of methane or equivalent. Then what we will have 3 degrees of translational freedom plus 3 degrees of rotational freedom. Then it will have an associated energy of 6 times half kg. Here I remind you that for polyatomic gas, the degrees of freedom might be bigger than 5. It might be 6 or might be 7, might be more. What I write here corresponds only for the methane, okay? And molecules having the similar rearrangement than methane, then the degree of freedom will be 6, but it may be more. Then, if we want to generalize, we can write the change in internal energy by the number of freedom that the molecule has. Then we can have this expression. We we'll have F over 2 times nRT. Good. Once we have this, we replace into the formula to calculate the CV. Then we should have a new expression of CV following the degrees of freedom. 4.16 F. CV equal 4.16 F. Okay. Here I summarize the degrees of freedom of our molecules and the predicted molar specific heats. For example, monatomic gas, we have this value and this value. You see it already because the degrees of freedom of a monatomic gas, you know that is 3 translational kinetic energy, 3 translational freedoms, degrees of freedom. For diatomic gas, we have this one. Okay, and for polyatomic gas, we have this one. Good. Now you see the link between the degrees of freedom and the molar specific heat. Is it okay? We stop here for the molar specific heats. We continue to another very important part, and this is also the last part of the kinetic theory of gases that I want to share with you. We consider the adiabatic expansion of an ideal gas. Adiabatic expansion of an ideal gas. Okay. Now we reconsider our system of a cylinder, right? Contain an ideal gas. We've seen it in the first part already. Here we have the lead shot. This system is very well insulated. So we have a closed system. Okay. We know that if we remove the lead shot slowly, very slowly, we will have an expansion without any heat transfer. Then we have an adiabatic expansion. Please remember that an adiabatic expansion is that an expansion that has no heat transfer, right? So the heat equals 0, no heat transfer. Đoạn nhiệt, đúng không ạ? Một chu trình đoạn nhiệt các bạn nhớ là nó không có sự trao đổi nhiệt năng. Good. And in the PV diagram, an adiabat is also a curve like this. Yeah. Please do not make mistake. Do not be confused with isotherms. In isotherms, we also have a curve. So sometimes when I ask you to establish the PV diagram, you will make mistake between an adiabat and an isotherm. Please do not make mistake. You cannot tell, except you have enough information to establish it. Yeah. Or people tell you that this is an adiabat or this is an isotherm. Otherwise, if you just look at the curve, you cannot tell that this is an adiabat or this is an isotherm. Okay, do not make mistake here. Nhiều bạn mà khi làm bài ấy, các bạn hay nhầm, các bạn cứ thấy cong cong thì các bạn nghĩ là đường đoạn nhiệt hay là đường đẳng nhiệt. Nếu như mà đề bài không nói thì thường là ta sẽ không biết nhé. Good. Now we apply the first law for a very tiny volume change at constant pressure. Constant pressure. Okay. Then we rewrite the first law in the form of differential. We have the differential internal energy equal the heat minus the differential work. Good. And at constant pressure, it becomes this expression Q minus P dV. Okay. Now we substitute the heat equals 0 because this is an adiabatic expansion. And the expansion of internal energy in the form of differential. Then we can write differential internal energy equal NCV delta dt. Okay. Then what we have is this one. This one is delta T. This one is the heat. This one is the work. We simplify this one. We should have an expression like this. And dt equal minus P over CV times dV. This one. Now we continue. We use the ideal gas law to replace the pressure. And remember, this is a little bit of mathematics. If we take the differential from both sides, now we have PV equal nRT. If we take the differential of the product of a product PV, what do we have? We have VdP plus PdV. So this is mathematics, okay? And here we have N and R. These are constant. We have only dV. Các bạn nhớ nhé. D của cái tích này PV này thì sẽ phải bằng là VdP cộng với PdV. Này là toán đúng không ạ? Các bạn nhớ hộ tới cái phần toán này nha. Good. And please also write it down. Follow me and you use a pencil, you write it down. Do not just look at the slide. It will be very hard for you to follow. Please write it down. Bạn Thảo có đây không nhỉ? Nguyễn Phương Thảo. Nguyễn Phương Thảo. Tôi không thấy camera chuyển động gì cả. Then, once we have this expression, we substitute also the gas constant. Now we know that the gas constant is equal Cp minus Cv, right? We just developed it. Then we rewrite the N dt here. This will have this expression. Please write it down. Sometimes I make mistake, okay? Verify with me. But this time I think it's correct. We can rewrite it. We continue. Here, in the previous slide, we already have an expression of N dt. This one. Now we know that this one equal to this one. We just developed it. We know that this one equal to this one. Now we simplify it. We simplify Okay. What will happen if we simplify it? This you see here. Here we have P dV here. If this multiply with CV here, then we have exactly P dV here. And here we also have P dV. Then we can cancel out the two P dV here. What is left? What is left is this one only. Good. This is what is left. So, okay. We continue. Now I call it gamma, the ratio between CP and CV. We often call the ratio between the molar specific heat at constant pressure and molar specific heat at constant volume gamma. And it has a value of 1.4 if you do a little bit of calculation. So 1.4, yeah, for the monatomic gas. Okay, now we substitute the gamma and we integrate. You see here, we integrate our final expression here. What will happen if we integrate the dP over P? We will have the ln P. Okay, this is mathematics. Please do not ask me why. You should be able to do this very simple formula of mathematics for the integral. Then we have ln P plus gamma ln V. And this one equal a constant because here the zero, if we take the integral, it should be a constant. Good. We rewrite it. Actually, the two ln's plus, yeah, together, we can rewrite as the product. The product. So we have this one. We just rewrite this. We just rewrite it. Okay. Now, once again, now we add. We want to remove the ln. Okay. Then we put it as the power of the exponential. And this, even we put it an exponential here, what do we have? A constant remains a constant, right? Of course, this constant is different than this constant, but it is still a constant. In this way, we can remove the ln here. Finally, we can write the PV power gamma is a constant. You follow me? Tuấn Đạt, you follow me, right? Bạn Nguyễn Tuấn Đạt. Chỗ này vẫn ổn chứ gì, vẫn hiểu chứ gì? Không nghe thấy gì. Bạn nào mà đi vệ sinh không cần phải xin tôi đâu, cứ đi nhé. Good. And if we consider a process having an initial state and the final state, we apply in this expression. What do we have? We have we have this expression. This is applied for the initial state, and this is applied for the final state. Is it okay? So this is one expression that you should remember. Pi Vi power gamma equal Pf Vf power gamma. We can also express it as a function of temperature and volume. Here we express it as a function of pressure and volume. We can express it also as a function of temperature and volume. We substitute the pressure by this form. So this is actually the ideal gas, right? Now we substitute here, the pressure from here to here. We have an RT V power gamma over V is still a constant, right? And what we see here, but NR, we put it to your right. V here, it will become V power gamma minus 1. Then what we have is that T V power gamma minus 1 is still a constant. Is still a constant. Do you agree with me? Then if we apply to our process, we can write it like this. Ti Vi power gamma minus 1 equal Tf Vf power gamma minus 1. So this is another expression that you should remember. Another expression that you should remember, okay? Here, there's one special case. Do you remember the free expansion? This is also an adiabatic process because there's no heat transfer during a free expansion. But we cannot apply the above equations. We cannot apply because we cannot have the relationship between the initial state and the final state. Actually, in the PV diagram, if you want to express the free expansion, is only 2 dots and there's no link between the 2 dots. Okay, there's no link between the 2 dots. And if you replace into our internal energy, for example, you should have the Ti equal Tf for an adiabatic free expansion, right? The change in internal energy equal NR delta T. But we know that the change in internal energy of a free expansion equals 0. Then we should have the change in temperature equals 0. And then we know that the Ti equal Tf for an adiabatic free expansion. Good. Nếu như mà các bạn biểu thị cái free expansion ở trên cái PV diagram, một sự giãn nở tự do ở trên cái biểu đồ PV này, thì nó chỉ là 2 cái chấm đấy. Cái đấy là cái tôi đang giải thích nhé, 2 cái chấm mà nó không có mối liên hệ giữa 2 thằng. Tất cả các thằng bằng 0 mà. Và nếu như mà chúng ta xem xét là cái delta E bằng NR delta T ấy, thì delta E thì nó bằng 0 mà. Thì chúng ta sẽ thấy là delta T nó cũng bằng 0. Và khi nó bằng 0 thì chúng ta biết là TI nó sẽ bằng TF. Đó. Cho nên là các cái biểu thức ở trên đây chúng ta không thể áp dụng được cho cái trường hợp free expansion. Nhưng free expansion thì chúng ta biết là nó rất là dễ. Ok, I think we can take a break, small break of 5 minutes here. I will go to drink something, 5-10 minutes. And then finally we will finish this part and also this chapter.
Okay.
Resume. Then we continue until the end. Này bạn nào có cái avatar mà con mèo to đùng ấy nhỉ? Con mèo khổng lồ nấp sau cái tòa nhà. Please come back. Yeah, I'm verifying. Okay, hiện anh này. Good. Khương Tự Duy đâu ấy nhỉ? Khương Tự Duy quay lại chưa?
Ở đây em bật ạ.
Okay. Nguyễn Phương Thảo quay lại chưa? So we continue here. We should remember the adiabatic expansion of an ideal gas. But we may have 4 special processes that an ideal gas can undergo. Truly speaking, if you remember this table, you will be able to do well the exam. Okay, for special processes that an ideal gas can undergo, we have an isobaric process. This one we know already. Isobaric process, or we also call constant pressure process. Constant pressure process. What we have the heat done by this process can be written as NCP delta T. And the work is P delta V. This one you know, we've seen in the previous slides. This one you know in the even previous part. Okay, please remember that the change in internal energy can always be calculated using these formulas. This is the first law, okay? And this one is true for all parts. Good. For an isothermal process or constant temperature, we have this one. So the work equal the heat and equal this one, nRT ln Vf over Vi. This one you saw it already. And the change in internal energy equals 0 also. This is similar to a free expansion. Here, why? Because the change in temperature equals 0. Then the heat also equals 0. For the work, we already developed previously how to find this expression. I will not repeat it here. Okay. For the adiabatic expansion, then we have the constant quantity is what we seen in the previous slide. So we have P, V power gamma and TV power gamma minus 1. And then for adiabatic process, we have heat equal 0 and the work equal minus change in internal energy. So you see here, this is actually the combination of the first part when we study only the change in internal energy, and of the second part when we consider an ideal gas, okay, the kinetic theory of gases. Then we will have this table. We will have this table. For an isochoric process, then we have this one, the work equals 0, you know it, for special cases of first law, and the heat equal NCV delta T. Now the heat is this one, okay, the heat is this one. Good. Now I give you 5 minutes to do this exercise. And then after this exercise, I will summarize the whole knowledge that we have seen together for the second part, for the part of kinetic theory of gases. Because this is a big part, then I will summarize it. And then we finish this part. And for the next session, when we work together for the next lecture, we will study the second law, the entropy and the second law. Now for this exercise, we have an ideal diatomic gas. Okay, now we have a diatomic gas. It has an initial pressure, this one. This one is 2 bars, okay? And an initial volume on this one. Good. What we have to find is the work done by this gas. And also the change in internal energy. If this gas expands adiabatically to a final volume, this one. And throughout the process, the molecules have the rotation, but not oscillation. So this one is to be sure that we have only 5 degrees of freedom. You remember for diatomic gas. For diatomic gas, we have 3 degrees of translational freedom and 2 degrees of rotational freedom. Actually, in reality, it might have the oscillation, but for our ideal gas, we do not consider it. Then it has only 5 degrees of freedom. Please, 5 minutes. And if someone finished, you can share it to others also. Yes, if you do not remember the formula yet, we take a look at the notebook. Sao Trương Hiền Anh ở trong nhà mà cũng phải khẩu trang nhỉ? Cẩn thận quá. Có cả ảnh hồi bé để trên tủ kìa. những năng lượng thôi.
Dạ.
Để cái hình nền gì đấy?
Ngày trước em để em nghịch nhưng mà giờ em không biết thay ở chỗ nào.
Tôi nhắc nhở các bạn nhé. Đã có một trường hợp mà để hình avatar nhưng mà phản động rồi đó, mà thầy Khôi thầy thấy và thầy cũng báo lại rồi đó, thầy báo lại ban giám hiệu và thầy cũng báo lại cả, bởi vì thầy có cả liên hệ bên công an các thứ nữa, cho nên là các em cũng phải rất là cẩn thận.
Vâng.
Chúng ta nghịch, đôi khi chúng ta lại không biết hết cái ý nghĩa của nó đó. Mà nhất là ở cái thời đại này mà các bạn lại chụp lại rồi bạn này thấy hay bạn kia thấy hay thì nó sẽ trở nên rất là nguy hiểm. Có thể nhiều khi các em lúc đưa lên các em chỉ nghĩ là nghịch thôi, nhưng bởi vì các em đã qua 18 tuổi rồi đó, các em trở thành công dân rồi, các em chịu trách nhiệm trước pháp luật rồi, thì lúc ấy thì các em phải nhìn nhận lại những cái vấn đề này nó thực tế hơn, mà nó ấy hơn, nó nghiêm túc hơn đi. Rất chú ý với những các cái hình ảnh trên avatar trên Facebook, rồi cả lời nói nhé. Tuổi này là đi tù được rồi, đừng nghĩ là mình vẫn còn bé. Good. Does someone have the solution and you can share it to others? Lê Như Ngọc xong chưa? Lê Như Ngọc xong chưa?
Em vừa bị out.
Lê Như Ngọc xong chưa?
Chưa.
Chưa. Okay, I will correct it. It takes so long. Now, what we see. This is what we see. We have an ideal diatomic gas. We have the initial pressure, initial volume, final volume, and we have the gamma. The gamma for diatomic gas equal 1.4 because the CP is 7R/2 and the CV is 5R/2. This one, you know, right? This is for diatomic gas 1.4. Good. Now for the work done by this gas, how do we calculate? We can start with this general formula. This one is always true, okay? We've seen it during the first chapter or first part, I mean. Good. The integral from VI to VF of PdV. We have to find an expression of P, right? And since this is an adiabatic expansion, we have this one, PV gamma is a constant. Then, at any moment, we can write PV gamma equal the initial state PIVI power gamma. This is true, okay? At any moment, we have this one. Now we do not consider only the final state, we consider the at any moment. We have PV power gamma equal PIVI power gamma. And the pressure P can be written in this form. Do you agree with me? Any question here? Good. We replace this expression of pressure into this formula. Then it becomes solving this expression. What we have pi vi power gamma is a constant. Okay, we take it out from the integral. It becomes solving the integral, this integral. Is it okay? And for this integral, we apply the mathematics, a little bit of mathematics. This one is actually this one. Yeah. Các bạn nhớ công thức toán không ạ? So you should remember the mathematics here. Then you should be able to develop this integral and it will become this one. If you still do not remember, I give you 1 minute to check the formula in mathematics. Đúng không ạ? Nếu mà các bạn phải nhớ cái này, các bạn phải nhớ giải toán đây, mà nó cũng không khó. Các bạn xem hết rồi. Tốt nghiệp được thì chắc là cũng nhớ giải được cái này. And if you replace everything correctly, okay, pi vi vf over here, you should have this final result for the work. If you place it correctly, okay, really pay attention on the unit. Good. And finally, we apply the first law. Then we should be able to find the change in internal energy. It has a minus here, meaning that the system loses energy to do work. Is it okay? Good.
Yes.
So to summarize, yes. To summary, we have seen a lot of things in the kinetic theory of gases. Then I summarize here. Firstly, the concept of kinetic theory of gases. This is a concept to relate the macroscopic properties. We have pressure, temperature, and so on, volume. To microscopic properties, we have the volume, the change in internal energy. We learn the ideal gas law, okay, PV equal nRT. So when you do the exam, for example, you see the word ideal gas, you know for sure that we should apply this one somewhere, the PV equal nRT. So this is the first law, the ideal gas law. We know that the work done by an ideal gas, and we consider 3 special cases: the work done by an isothermal expansion or compression, the work done by a constant volume, okay, Isobaric process, the work done by a constant pressure, Isobaric process. You should be able to remember it. Then the relationship between the pressure, the temperature, and the speed of molecules. We have different kinds of speeds, of course. We have the most probable speed. We have the average speed. We have the root mean square speed. Yeah, please remember. Then we have the temperature and the kinetic energy. We can write the translational kinetic energy as 3/2 times kT. So K is the Boltzmann constant. So it means that if we know the temperature, we can also calculate the kinetic energy of the molecule or of the gas in general. And the mean free path. So the mean free path is actually the average distance that the molecule can travel between the collisions. Okay. So this one, it depends on the temperature and on the nature of the gas, on the molar mass of the gas. The Maxwell distribution, the very heavy function that now I'm thinking of excluding this part from the exam, but you should still remember it. Then the molar specific heats, we have molar specific heat at constant volume and molar specific heat at constant pressure. You should also remember it. It will be a big part, a very big part for the tutorial and also for the exam, the molar specific heats, and its a relationship with others. And finally, the degree of freedom and CV with the small v, I make a mistake here, the degrees of freedom and the molar specific heats. Finally, the adiabatic process of an ideal gas. Okay, adiabatic process of an ideal gas. And also all the special cases, because for all the cases you already seen in the first part. Yep. Now we summarize everything. Yeah, we combine with the second part. Then we have four special cases. But the adiabatic process of an ideal gas is something new. We already seen it here. So this is the whole concepts, laws, and so on of the kinetic theory of gases. Okay, so you see this part is a very big part. That's why it took us 2 sessions. Please, I uploaded already the slide on Moodle. Please take a look at it. We have another session for the tutorial, and then we will see, I think, from the mean free path until the end, because last time we already see the ideal gas, the work done by an ideal gas, a little bit of the pressure, the relationship between pressure, temperature, and molar speeds. We will continue the whole things here to here in our second tutorial session. Okay. So if you have any questions.
May you have the plan for midterm test?
Yeah, for the midterm, we will have the last lecture, and after this last lecture, next week, I mean, before
the third, right?
The third holiday, exactly, I will try to set a midterm exam, also a very short midterm exam, like the mechanics. So I will give you, I'm considering maybe less questions. I know that you have 30 questions for the mechanics, right? For 20 minutes only.
And
I was 13. I was fast.
Yeah. So was it okay?
Nope.
No,
Not at all.
no.
I think you should soon do like this.
Maybe I will. Okay, then I will try to reduce. I will try to reduce questions in this part, but it will take on so only 20 minutes. very quick, okay? And I will try to give you simple thing. If you reread my slides, you should be able to have the answer in 10 seconds. Yeah.
I think the question will, lower than the minute.
Yes, maybe 1 minute, one question, maybe a little bit more, but I try to do something that is easy for you.
No, I think it's not easy.
Don't worry. Firstly, because you study online, so I think it should be harder for you already. If you have the occasion to study things like this offline, then I can also control better the class, and you can also stay more focused on the lesson. Of course, the slides will be the same, but I will have more time, for example, explaining things using the board, or I can verify if some of you still do not understand. But because we study online, so maybe there are some things you cannot capture. Then I will try also to simplify a little bit of the exam. So don't worry about it, okay? The purpose is that you stay focused on the thermodynamics. You understand the basic concept. You can apply the concept into some real exercises, some real applications. Then that's all. So I do not want to give you something that is really hard for you. So it is for nothing. Okay, and please remember that the small test is only one part of the midterm. The other part is your participation already during the tutorial class. So I think today we finish, and thank you very much. We will see each other maybe in the tutorial part and maybe in the last part when we talk about the entropy and the second law. Thank you. I think you can stop now. Thank you for standing with me. See you.
Goodbye.
Goodbye, teacher.
Goodbye.
See you. Bye bye.
You next time, teacher.
Bye bye teacher.
I
See you.
I heard that.